Commander Buell Hansen stands behind his sonar operator in USS Tautog's control room, watching the waterfall display track a Soviet November-class submarine 200 yards ahead. The operator's hand stops above the bearing dial. K-108's blade rate is dropping fast, bearing rate swinging left. The Soviet boat is executing a clearing turn, rotating its bow toward Tautog's position to unmask the stern blind spot both captains know is there. Hansen's boat weighs 4,600 tons and carries forward momentum even as the helm answers back full. The geometry is simple and unforgiving. Tautog is still drifting into the turn radius with no time to stop, no room to dive, and no way to reverse 4,000 tons of inertia in the 15 seconds before the hulls meet. June 1970. Tautog is running a special operation 12 miles off Petropavlovsk, the Soviet Pacific Fleet's submarine stronghold on the Kamchatka Peninsula. Her mission is to intercept boats leaving port and log their acoustic signatures: blade rate, shaft RPM, hull flow noise, anything naval intelligence can use to identify individual submarines in open ocean. The crew has been tracking K-108 for 6 hours, holding station 2,500 yards astern, inside the narrow cone where Soviet passive sonar cannot hear them. Every few minutes, the sonar operator updates the plot. Target speed 8 knots, course steady. No indication the Soviets know they have company. This is exactly what the mission requires, and exactly why it is dangerous. Tautog operates under emissions control. No active sonar, no radio transmissions, minimal course changes. The sonar team relies on passive arrays mounted along the hull, listening for the faint hiss of cavitation bubbles collapsing on K-108's propeller blades. Active sonar would give them range and bearing in seconds, but it would also announce their presence to every Soviet hydrophone within 50 miles. So they track by ear, correlating blade counts with known propeller configurations, updating the fire control solution every 30 seconds. The process is slow and requires the target to cooperate by holding a steady course. If K-108 turns without warning, the geometry collapses, and Tautog's crew has seconds to react or lose contact entirely. Soviet submarine doctrine includes a routine maneuver called the clearing turn, a hard rudder reversal designed to unmask the stern blind spot and catch any trailing NATO boat off guard. Every Soviet captain learns it, and every American tail knows to expect it. The problem is timing. A clearing turn generates no warning, no radio call, no blade rate spike, just a sudden bearing rate change as the target's bow swings toward you. Tautog's crew has seen it before on other patrols. They know the geometry. When the target turns, you either fall back fast enough to stay outside his sonar cone, or you risk detection. Today, with only 200 yards of separation, falling back is no longer an option. American submarine intelligence depends on recording propeller signatures at ranges under 3,000 yards, where thermal layers and Soviet noise masking degrade long-range passive sonar. At 2,000 yards, Tautog can count individual blade passes and measure cavitation onset speed, data that lets analysts identify a specific boat by its propeller alone. At 5,000 yards, the same target sounds like distant rain. Naval intelligence needs the close-in recordings to build a library of acoustic fingerprints for every Soviet hull in the Pacific Fleet. That requirement pushes crews into the same waters Soviet captains are trained to defend, creating a tactical paradox. The closer you get, the more valuable the intelligence, and the less time you have to avoid collision. Every submarine trails a 30-degree acoustic blind spot directly astern, called the Baffle Zone. The boat's own propeller noise, hull turbulence, and machinery transients completely mask external contacts in that cone. Soviet and American sonars are equally deaf in the baffles. For Tautog's crew, staying inside that cone is survival. As long as they remain in K-108's baffles, the Soviet sonar team hears nothing. But the cone is narrow, and it moves with the target. A 5-degree course change can unmask Tautog in seconds. The only way a submarine captain can check his baffles is to turn hard enough to rotate the blind spot through the area astern, exposing any follower. It is a simple tactic, and it works every time someone is actually there. Soviet captains train on a maneuver American submariners call the Crazy Ivan, a snap helm reversal with no warning, designed to catch trailing NATO boats before they can react. It is not reckless, it is doctrine. The captain orders hard left or right rudder, the boat heels into the turn, and the sonar team listens for any contact that was hiding in the baffles. If they hear nothing, the captain steadies on the new course. If they hear propeller noise or a hull transient, they know they had company and can prosecute or evade. The maneuver works because American tailboats cannot predict it. Sonar might detect blade rate changes or rudder-induced flow noise 10 to 15 seconds before the turn completes, but that delay leaves almost no margin to clear the collision triangle. Tautog's sonar can track blade rate and shaft RPM, but it cannot hear helm orders. The Soviet captain might decide to clear baffles every 30 minutes, every hour, or whenever instinct tells him to check. The Americans have no algorithm, no pattern, no way to anticipate the turn until it is already underway. By the time sonar detects the bearing rate change, K-108's bow is already swinging toward Tautog's position. At 8 knots and 200 yards, the reaction window is 15 seconds or less. Hansen's crew is trained for this scenario. They know the procedure. Emergency back full, hard rudder away from the turn, hope the geometry opens before the hulls meet. But training assumes enough separation to make the procedure work. June 20, 1970, 0340 hours. The sonar operator reports blade rate dropping on K-108, bearing rate accelerating left. Contact is turning toward them. Separation is under 200 yards. Hansen orders emergency back full and right full rudder. The helmsman repeats the order and spins the wheel hard over. The diving officer adjusts trim to counter the rudder-induced list, but Tautog's 4,600 tons do not stop on command. Her propeller bites in reverse, her bow starts to swing right, but inertia keeps her drifting forward into the space K-108 is now rotating through. The sonar display shows the two bearing lines converging. No one speaks. There is nothing left to say, and nothing left to do. K-108's keel strikes Tautog's sail at a combined closing speed near 8 knots. The collision generates a sharp metallic screech that travels through both hulls, audible in every compartment. Tautog's periscope shears buckle inward. K-108's bronze propeller catches on the American boat's fairwater, and a section of blade fractures, tearing free and embedding in the superstructure. The impact lasts less than 2 seconds. Then both boats break contact, diving away from each other in opposite directions. The sonar displays go blank. K-108 disappears into the thermal layer to the northwest. Tautog steadies at 400 feet, damage control teams checking seals and reporting flooding. The control room is silent, except for the hum of ventilation and the faint ping of hull stress relaxing. The 10-inch section of K-108's propeller is wedged into Tautog's fairwater, held in place by the deformed steel and the fragment's own jagged edges. It is cast manganese bronze with traces of nickel aluminum alloy, a metallurgical signature unique to Soviet naval foundries. For naval intelligence, the fragment is a prize. Propeller composition reveals manufacturing limits, acoustic performance, and maximum speed envelope for the entire November class. For Hansen, it is evidence of a collision both governments will want to deny. If the fragment falls off during the 5,000-mile transit back to Pearl Harbor, the proof disappears. If it stays attached, someone has to document it, secure it, and explain it without leaving a trail in unclassified maintenance logs. The collision transferred kinetic energy into local hull deformation. K-108's propeller blade was cast manganese bronze with nickel aluminum alloy, designed for corrosion resistance and acoustic damping, but vulnerable to brittle fracture under lateral impact. The blade fractured at a stress riser near the hub, where thickness transitions from root to tip. Tautog's sail is fabricated from HY80 steel, a high-yield alloy developed to withstand depth-charge shock. The steel bent inward under the impact, but held pressure integrity. The fragment itself weighed roughly 8 pounds and measured 10 inches along the leading edge. Its embedment in the fair water created a secondary problem. The jagged trailing edge acted as a flow disruptor, generating low-frequency noise that Soviet passive sonar could detect at longer range than Tautog's normal acoustic signature. The embedded fragment created two problems. First, it confirmed a collision with a Soviet boat. Metallurgical analysis would identify the alloy composition, trace elements, and foundry signature, linking the fragment to the Soviet naval supply chain and likely to a specific submarine class. Second, the fragment risked falling off during transit. 5,000 miles of ocean, variable sea states, hull flexing, and thermal cycling could work the metal free. If it fell off before Tautog reached Pearl Harbor, the physical proof disappeared, and the Pentagon could deny the collision ever happened. If it stayed attached but was not properly documented, naval intelligence would lose the metallurgical data and acoustic signature analysis that justified the mission in the first place. The fragment had to be secured, photographed, and logged, without generating paperwork that could surface in unclassified channels. Tautog's damage control officer, Lieutenant Commander Joseph Vasey, organized an underwater documentation effort. Divers using handheld cameras in waterproof housings photographed the fragment from 6 angles, capturing the embedment depth, fracture surfaces, and surrounding hull deformation. They measured the fragment with calipers, logged its position relative to hull frames, and drafted a sketch showing the impact geometry. Then they secured it. Vasey's team welded a steel retaining bracket around the fragment, threading stainless wire through pre-drilled holes in the fair water and twisting it tight enough to prevent movement without applying pressure that might crack the bronze further. The entire operation took 4 hours and was conducted at periscope depth in international waters. No record of the work appeared in the ship's unclassified maintenance log. Soviet propeller samples were among the highest priority intelligence targets in the Cold War. Blade pitch determined maximum speed. Cavitation resistance revealed acoustic signature at sprint. Alloy composition indicated manufacturing tolerances and foundry capacity. A single propeller fragment could validate or refute sonar-derived performance estimates for an entire submarine class. The manganese-bronze alloy in K-108's blade told analysts the Soviets were still using 1950s foundry techniques, limiting sprint speed to roughly 28 knots before cavitation noise overwhelmed any attempt at stealth. That intelligence fed directly into American torpedo engagement envelopes, patrol box sizing, and strategic assessment of Soviet second strike capability. The fragment was quietly transferred to naval intelligence when Tautog reached Pearl Harbor. It was never mentioned in official damage reports. Tautog had no dry dock access for 5,000 miles. The nearest facility capable of hull inspection and structural repair was Pearl Harbor. Until then, Vasey's improvised steel bracket and wire lashing had to hold. The crew monitored hull integrity at 6-hour intervals, checking for leaks, measuring vibration levels in the sail structure, and listening for any change in flow noise that might indicate the fragment was working loose. They logged GPS coordinates at the moment of collision and drafted a classified damage report for SubPac that detailed the fragment's position, probable origin, and intelligence value. That report went into a special access compartment within the Submarine Command's classified filing system. It never entered unclassified maintenance logs, never appeared in shipyard work orders, and was not mentioned in Tautog's official patrol summary. May 1974, Sea of Okhotsk. USS Pintado is at periscope depth, trailing a Yankee-class ballistic missile submarine. The mission is the same as Tautog's 4 years earlier. Log acoustic signatures, track patrol patterns, stay undetected. Sonar reports a new contact bearing 090, range 1,200 yards, closing at 30 knots, directly ahead. The officer of the deck cross-checks the display. The contact is not the target they have been trailing. It is a second Soviet boat inbound from Petropavlovsk, and the geometry is simple. Both submarines are on converging courses with less than 60 seconds to impact. The dive officer waits for orders. The helm waits for orders. No one has 60 seconds. They have less than 40. The officer of the deck has 2 options. Emergency deep. 90 seconds to clear periscope depth and drop below the collision plane, but that assumes full ballast blow and negative trim, neither of which can be executed in less than 60. Emergency back full and hard rudder. 15 seconds for the propeller to bite and the hull to respond, but minimal lateral displacement at periscope depth, with no forward speed to trade for turning radius. Neither option clears the collision triangle. The closing speed is 30 knots combined, the range is 1,200 yards and shrinking, and the Soviet boat shows no indication it has detected Pintado. The officer orders emergency back full and hard right rudder. It is the only move that might create separation, and it is not enough. Pintado's bow strikes the Soviet SSBN's bow at a combined speed near 35 knots. The impact crushes forward ballast tank sections on both boats, ruptures sonar dome fairings, and floods Pintado's forward trim tanks. The collision generates a shock wave that travels through both pressure hulls, throwing crew members against consoles and snapping unsecured equipment loose. Pintado's bow sonar array disintegrates. The Soviet boat's forward ballast tank vents explosive decompression as compressed air and seawater mix. Both submarines lose forward trim. Both commanding officers order emergency blow. Within seconds, both boats surface in the same patch of ocean, less than 200 yards apart. Then, both dive again, seeking depth and distance before visual identification becomes mutual. Both submarines leave behind a debris field, crushed steel, sonar rubber tiles, hydraulic fluid, fragments of ballast tank plating. Soviet ASW helicopters from Petropavlovsk reach the site within hours, photographing the surface slick and recovering floating debris. The debris includes pieces of American-manufactured sonar rubber and steel plate, stamped with U.S. foundry marks. Soviet naval intelligence catalogs the evidence but cannot identify the specific American boat, or confirm whether it was intelligence collection, navigation error, or deliberate harassment. The debris confirms an American submarine was operating inside Soviet patrol zones, but without a hull number or visual identification, it is not enough for a formal diplomatic protest. Both navies stay silent. Tautog limped back to Pearl Harbor with the propeller fragment still wired to her sail. The fragment was quietly transferred to naval intelligence, analyzed for alloy composition and blade geometry, then archived in a special access vault. It never appeared in official damage reports. K-108 returned to Petropavlovsk with visible propeller damage that Soviet divers photographed and documented. The missing blade section could not be explained by cavitation, fouling, or normal wear. The fracture surfaces indicated lateral impact with a hard object. Soviet naval intelligence suspected collision with an American submarine, but had no proof and no way to protest without admitting they had lost track of a trailing boat in their own territorial waters. Both navies filed the incident in classified channels and said nothing publicly. Pintado's collision required emergency repairs at Guam. Bow sonar components, ballast tank plates, hull steel, forward trim system valves. Each repair generated a requisition order, a parts delivery log, and a work completion report. The requisitions appeared in unclassified Navy supply systems because shipyard logistics cannot operate entirely in classified channels. But the mission context and damage cause were redacted from all maintenance records. Analysts reviewing the supply logs years later could see that Pintado received bow sonar parts and ballast tank steel in May 1974, but the reason field in every document read operational requirement or routine maintenance. The repairs were real. The explanation was fiction. The paper trail existed, but it led nowhere for 20 years. The Pentagon issued flat denials when asked about submarine collisions near Kamchatka throughout the 1970s and 1980s. Spokesmen cited operational security and refused to confirm or deny the existence of special operations in Soviet waters. Congressional inquiries received classified briefings with no public summary. Journalists who pressed for details were told that discussing submarine movements would compromise sources and methods. The denials were not lies in the narrow sense. No official would say the collisions never happened, but they were structured to prevent confirmation. As long as both the forensic evidence and the mission context remained classified, the collisions could be treated as rumor, speculation, or Soviet propaganda. The strategy worked for 2 decades. In the early 1990s, Soviet naval archives began declassifying damage reports and salvage logs as part of post-Cold War transparency initiatives. K-108's missing propeller blade and the debris field from the Pintado collision matched American submarine profiles: Sturgeon-class geometry, HY-80 steel composition, U.S. Sonar rubber formulations. Russian naval historians published damage photographs and collision timelines that aligned with gaps in American submarine patrol schedules. The forensic match was circumstantial, but compelling. By 1996, U.S. Navy historians acknowledged both incidents in declassified summaries, citing operational security constraints that no longer applied. The collisions moved from rumor to documented history, not because new evidence emerged, but because the classification barriers on both sides finally eroded. The collisions reshaped American submarine doctrine. Trailing distances increased from 2,000 yards to 3,500 yards minimum in high-traffic Soviet patrol zones. Clearing turn algorithms were refined. Sonar operators received new guidance on detecting rudder-induced flow noise and blade rate deceleration patterns that preceded snap turns. The term Crazy Ivan entered official tactical manuals as a formal threat procedure rather than submariner slang, with prescribed evasion steps and minimum safe separation. Training scenarios incorporated collision avoidance as a primary objective, equal to maintaining contact. The doctrine changes were not published in unclassified manuals, but they filtered through the submarine community and became standard practice by the early 1980s, years before the collisions themselves were publicly acknowledged. The Tautog and Pintado collisions proved that Cold War submarine intelligence was not a quiet, near-miss game. American and Soviet boats collided at least twice in Soviet waters, with enough violence to shear propellers and crush ballast tanks. Both navies denied it, until the debris trails became undeniable. A 10-inch propeller fragment archived in a classified vault, a debris field photographed by Soviet helicopters, repair requisitions that could not be fully redacted, and damage reports that matched across enemy archives. The collisions were not accidents in the civilian sense. Both were the predictable result of doctrine that prioritized intelligence over separation. The secrecy lasted 2 decades, but the evidence was physical, metallurgical, and bureaucratic. In the end, you cannot classify away the steel.